All right, get ready for the ultimate manufacturing battle. In one corner, we have titanium, one of the toughest supermetals on the planet. And in the other corners, three very different technologies, from ancient to sci-fi, all fighting to be the best way to shape it. Let's get into it.
So here's the central problem, right? How do you actually build something with a metal this tough? You can't just hammer it into shape. It takes some serious power and some incredible engineering. So, which method actually creates the strongest, most reliable titanium parts? That's the big question we're going to answer.
Here's how it's all going down. First, we're going to introduce our three main contenders. Then, we'll throw them into a head-to-head showdown, comparing the hard data. And finally, we'll deliver the verdict and crown a champion. Okay, so let's meet the fighters in this manufacturing Royal Rumble. What's so cool is that these three techniques basically represent the entire history of how we humans have worked with metal, from way back in the Bronze Age all the way to today.
Our first contender, casting, is the old-school champion with a history that goes back 6,000 years. Then you've got milling, born during the Industrial Revolution. And our final challenger is the high-tech newcomer, additive manufacturing, which really only hit the scene in the last 40 years or so.
Let's kick things off with the original titan of metalworking, casting. This is the classic, the OG method. The idea is simple. You melt metal down to a liquid and just pour it into a shape. The official definition is pretty much what you'd expect. You melt the metal, pour it into a mold, let it get solid, and then pop out your finished part. It's an amazing way to make really complex shapes that would be almost impossible to create otherwise.
You know, the basic idea is kind of like making Jell-O. You get your mold, you pour in the liquid, you let it set. We've been doing this for thousands of years. But with a super metal like titanium, the secret sauce is all in how you let it set. That part is absolutely critical.
So that cooling phase, that's where the real magic happens. As the liquid titanium cools down, it starts forming a crystal structure inside. These little branch-like crystals are called dendrites, and the way they grow literally determines how strong the final part will be. And our source material says it all right here. How fast you cool it changes everything. If you cool it slowly, you get big, chunky grains. Cool it fast, and you get small, fine grains. This grain size is a huge deal for performance. Remember that, because it's going to be key for our showdown later.
All right, on to our second contender, milling, the master of precision. Now, if casting is all about adding liquid metal to a mold, milling is the total opposite. It's about taking away solid metal from a block.
So, milling is what we call a subtractive process. You use these super fast spinning cutters to literally carve away material from a solid chunk of metal. It's all about precise, controlled removal, revealing the final shape that was hiding inside that block all along.
The best way to think about it is like a sculptor staring at a block of marble. The artist doesn't add anything, they just chip away everything that isn't the statue. Well, milling does the exact same thing, just with a block of titanium and some incredibly powerful computer-guided tools. And that brings us to our third and final contender, direct metal deposition, or DMD for short. This is the futuristic one, the high-tech process that isn't about pouring or carving, it's about building an object from absolutely nothing.
You've probably heard of 3D printing, right? Well, DMD is basically that, but for metal. It uses a super-focused heat source, like a laser, to melt superfine metal powders and build a solid object one tiny layer at a time. It's a totally different way of thinking.
So here's how it works. A powerful laser creates this teeny tiny pool of molten metal. Then, a nozzle sprays titanium powder right into that pool. The laser moves around, drawing one layer of the object, and it solidifies almost instantly. Then it just repeats that process, layer after layer after layer, until the whole part is built.
Okay, we've met our fighters. Now it is time for the main event, the performance showdown. We're going to look at parts made from the exact same titanium alloy and use the data from the study to see which process actually makes the better material.
First up, yield strength. This is how much stress you can put on the metal before it starts to bend and stay bent. And right out of the gate, look at that. The milled part takes a huge lead at over 1,000 megapascals. That's way higher than the other two. Round one, clear winner, milling.
Next up, ultimate tensile strength. This is the absolute breaking point. How much force can it take before it just snaps? And wow, again, milling just dominates, hitting over 1,100 megapascals. DMD is stronger than casting, but it's no match for milling. Another round goes to milling.
Okay, now for elongation. This tells us how much the metal can stretch before it breaks, a measure of its flexibility, or ductility. And, you guessed it, the milled part can stretch over 7%, more than double its closest competitor. It's a hat trick for milling. This is looking like a rout.
And finally, we have hardness, how well it resists scratching and denting. And whoa, just look at these results. They are absolutely staggering. Milled titanium clocks in at 760 on the Vickers scale. That is more than 10 times harder than the cast part. This is an absolute knockout punch.
So based on the numbers, this fight looks like it's over. I mean, milling completely crushed the competition in every single category we looked at. So which process really is the best?
On paper, milling is the undisputed champion. No question. It gave us parts that were stronger, more flexible, and just dramatically harder. But what if I told you that was not the study's final conclusion? That's right. This isn't the whole story. Not even close.
Okay, so here's the big twist. While the specific parts in this one test showed milling winning, the study's authors came to a very different conclusion. They realized that with DMD, you have a level of control that is just unheard of. Remember those crystal grains we talked about? With DMD, by tweaking things like the laser power and the cooling rate for every single microscopic layer, you can essentially design the metal's internal structure. From the ground up, you can fine-tune it to be perfect. The other methods have some adjustments, but DMD's potential for control is on another planet. And that led them to this stunning final verdict, and I'm quoting here. In comparison to casting and milling, the DMD process results in superior mechanical properties. The newcomer wins the title, not based on one fight, but on its ultimate potential and absolute control. This is a total game changer. We are literally moving from just shaping metal to designing its fundamental properties as we create it. It's the dawn of a new age in material science, and it leaves us with one heck of a question. Now that we can essentially print supermetals with whatever properties we want on demand, what impossible problems are we going to solve next?